Greeting, dear colleagues. My name is Mikhail Timchuk and I want to present my report on topic modeling, diagnostics and risk management in the leaching of a useful component from a man-made deposit, which I prepared with my co-authors Yaroslav Petrivsky and Volodymyr Petrivsky. The modern model of rational environmental management is based on the optimal use of man-made resources to preserve natural resources, reduce the cost of production of a certain useful component, but also for secondary ones. It should be noted that industrial waste is often close in composition and properties to natural materials, and in some cases has an advantage over it. At the same time, uncontrolled exploitation of man-made deposits and their chaotic existence turn industrial landfills into potential sources of environmental pollution due to the filtration of aggressive toxic substances into underlying rocks and mixing with groundwater. A well-known example of a site that can be considered a man-made deposit is the destroyed power unit of Chernobyl NPP. The most acceptable method of extracting the useful component is its infiltration leaching. The main objective of research is to develop an adequate mathematical model of hydrogeomechanical activation of the leaching process, allowing to optimize the reagent costs by choosing rational parameters of its infiltration, flow rate, and concentration. The main idea for the activation of physicochemical processes during leaching are based on the following ratio of permeability and correct opening in the massive. The next slide shows this relation in a graphical form, where there is a sharp quantitative jump between the parameters of permeability and crack widths. One of the effective ways to combat the negative impacts of industrial waste accumulation on the environment is the construction of various types of protective anti-filtration structures. Our proposal is to create a protective anti-filtration collector complex ACC that provides protection of the subsoil from the penetration of toxic substances, collection and delivery to the surface for processing and disposal of liquid technogenic waste. The main element, according to the technological scheme on the slide, is a system of underground mining workings, an inclined opening working 1, main 2, and section workings 3, which provides the opening of the underlying area and allow to create a protective collector screen in the subsoil, which provides directed gravity collection of technogenic solutions containing aggressive chemical or radioactive components into a collector made in the form of ZAMP6. At the stage of opening the underlying layers, the pumping equipment is used for water drainage, and at the stage of operation of the ACC for the delivery of technogenic solutions to the industrial site for processing and further utilization. The efficiency of hydrogeochemical activation of the process of leaching was assessed by modeling one-dimensional vertical non-stationary migration of a two-component mixture leach solution useful component, where 1 is leaching solution, 3 fracture cracks, 4 saturated productive solution. The mathematical model of the leaching process is a system of mass transfer equation 2-5 under condition of non-equilibrium kinetics. This equation reflects the pattern of decreasing leaching rate in the technogenic massive in the vicinity of the crack surface. The experimentally confirmed dependence of the increase in mass transfer intensity of the filtration rate is taken into account. The initial and boundary conditions for the system 2-5 are formulated in the following form 6-9. These conditions correspond to the equality of convective flows and insignificant diffusion of these substances flowing from the fractured rocks into the underlying deposits, which is acceptable at a high filtration rate. The system of equation 2.9 was solved by the finite difference method using the stable implicit scheme with the developed calculation program. Created software was developed with the .NET 8 framework and Windows Forms that provides simply user-friendly interface. The software system is organized according to a three-layer architecture comprising the presentation, business logic, and data layers. User interaction is performed through a VPF-based graphical interface, which provides parameter input and visualization of simulation results. Configuration data serve as input to the mathematical model, ensuring consistent execution of simulation, optimization, and diagnostic procedure. The initial data for modeling and estimation of technological parameters were selected for the technogenic uranium deposit at the Chernobyl NPP asset site. In accordance with the proposed scheme of infiltration leaching, the main part of the useful component is expected to be extracted within 3-5 years. During this period of time, according to the experience of developing uranium deposits with a low U content in the rock, at least 80% of uranium passes into solution from the solid phase. The filtration rate in full containing masses depends on their permeability and the flow rate of the supplied reagent. In the adopted leaching scheme, it corresponds to the flow rate of gravitational water supplied by hydraulic monitors to the surface of the full containing masses, which occurs at a gradient close to unity. Before hydraulic fracturing, the filtration rate cannot exceed 0.1 meters per day. After hydraulic fracturing, the rock filtration coefficient increases, resulting in a filtration rate in the range of 0.3–0.6 meters per day. A complete numerical analysis of the process is impractical due to the significant number of parameters whose reliable values cannot be determined. Therefore, the purpose of the modeling was to obtain numerical estimates of the main leaching characteristics in the range of known values of the process parameters for the development of this deposit. The modeling results are presented on the next slides. The graphs on the slide illustrate the change in concentration during the leaching of uranium as a function of depth Z without preliminary fracturing. Curve 1 shows the concentration N of uranium in the solid phase. We can see that after a year of leaching, the concentration of uranium in the solid form near the surface is still quite high, about 600 grams per ton. With increasing depth Z, this concentration gradually increases, approaching a value about 720 grams per ton at Z is equal to 10 meters. Curve 3 depicts the concentration of uranium in the dissolved form. Starting from a low value around 0 at Z equal 0, the concentration of dissolved uranium increases with increasing depth. This is expected as the solution passing through the ore body dissolves uranium from the solid phase, increasing its concentration in the solution. At the outlet, the concentration of dissolved uranium reaches approximately 9 grams per liter. Curve 2 represents the concentration of the reagent as a function of depth Z. The initial concentration of reagent is high, around 10 grams per liter. As the solution progresses deeper into the formation, the concentration of the reagent decreases. So the rate of change of concentration is highest in the initial stage of the process and slows down with depth, which may be due to the decrease in the content of easily accessible uranium and the reduction in the concentration of the reagent. We can also observe that in 15 years, at a depth of 5–6 meters, the uranium concentration decreases by about 3 times, while at greater depths it still remains almost the same as at the beginning of the leaching process. Next slide presents two graphs. A and B corresponds 1 to 1 and 5 years after the start of leaching with low impact pre-fracturing. As we can see, 1 year after the start of leaching, the concentration of dissolved uranium line 3 increases more evenly, which indicates better disclosure of the massive and more efficient leaching. The concentration of uranium in solid form is also somewhat lower, although no significant differences are observed. The concentration of the reagent decreases more slowly than in the previous case, which indicates approximately the same intensity of reactions at different depths. In graph B, we see that after 5 years of leaching in this mode, the concentration of uranium in solid form and in solution is significantly reduced at all depths, which indicates that the majority of the reserves will be extracted during this period. Thus, prior hydraulic fracturing significantly enhances the efficiency of in situ uranium leaching. This is evident to faster uranium dissolution, more effective uranium extraction, faster reagent consumption. This image shows the concentration distribution during uranium leaching with prior high impact hydraulic fracturing after 1 year A and 3 years B. Compared to previous case, we notice that after 1 year of leaching at a depth of up to 4 meters, a significant part of the uranium is extracted, and after 3 years, its concentration in the solid phase at a depth of 10 meters drops to about 400 grams per ton. As the table shows the estimated values of intensification of the process of leaching, containing efficiency indicators for both the undisturbed massive and the massive after hydrogeomechanical impact. As you can see, the previous hydraulic fracturing of the formation gives a rapid increase in the leaching rate, while its further intensification does not cause such a significant increase. Therefore, the optimal leaching process with low-level hydraulic fracturing can be called. In this mode, half of the reserves can be extracted in 2.75 years. So, during the research, it was established that when hydraulic fracturing affects rocks of a man-made deposit, there is a sudden increase in the rate of leaching of the useful component due to an increase in the permeability of rocks and the area of their contact with the reagent, which allows optimizing reagent costs by choosing rational parameters of its filtration flow rate and concentration. The intensity of leaching with hydraulic fractures in the massive increases several times over 5 years compared to the massive without hydrogeomechanical activation. Using the developed model allows to optimizing reagent costs by choosing rational parameters of its infiltration flow rate and concentration. Thank you for your attention.